Identify the voltage. Stabilizer based on the defects. Identify the defects in emergency light. Rectify the defects by repairing the emergency light. Analyze the fault in the UPS. Rectify the fault by repairing the UPS. Let us take a look at the tools and instruments required for testing, analyzing defects, and repairing voltage stabilizer, emergency light, and UPS. Tools or instruments. Trainees toolkit, 1 set. Connector screwdriver set, 1 set. Line or neon tester, 500 volt, 1. Soldering iron, 35 watt by 250 volt, 1. Desoldering gun, 1. Multimeter, analog or digital, 1. Clamp on meter, 1. Equipment. Common UPS 625 VA by 12 volt, 1. Sealed lead acid battery with operation manual, maintenance free battery, 12 volt by 120 ampere hour, 1. CRO 20 MHz by dual trace, 1. Assembled circuit of voltage stabilizer to be checked. Assembled circuit of emergency light to be checked. Assembled circuit of online UPS to be checked. Materials or components. Spare components as required. Solder 60 by 40 as required. Soldering flux as required. Connecting wires as required. Let us take a look at the preparations for testing, analyzing defects and repairing voltage stabilizer, emergency light and UPS. In this exercise, our first task is to analyze the fault and repair of voltage stabilizer with the help of a service flow sequence, SFS. Collect all relevant information about the voltage stabilizer, such as its make, model and specifications. Also gather any available documentation and troubleshooting guides. Start by performing some initial checks to identify obvious issues. Conduct a thorough visual inspection of the voltage stabilizer. Look for any signs of physical damage, loose connections or burnt components. Check for bulging or leaking capacitors, broken wires or damaged PCB traces. If any issues are found, they may need to be addressed during the repair process. Check the circuit carefully for any short circuit in the components or parts in the stabilizer. Connect the AC main supply cable of the stabilizer unit into the ohm meter and check the resistance by switch on the circuit. If it shows zero resistance, it indicates a dead short. Verify that the input voltage is within the stabilizer's specified range. Check for any open circuit visually or by ohm meter after testing for a short circuit. If the meter shows infinity, that is open circuit. If it is a healthy circuit, it will show some resistance reading. Analyze the status of the circuit by the meter's reading. If the stabilizer is without short circuit fault, connect it to the supply mains and switch on. Based on the symptoms observed during the testing, identify the potential fault areas. Refer to the troubleshooting guide for common issues associated with the stabilizer. Some common faults in voltage stabilizers include faulty voltage regulators, defective capacitors, open or short circuits, or overheating components. Check the symptoms of the unit and record the symptoms. Analyze the fault with the help of the service flow sequence. To further isolate the fault, perform component level testing. This involves checking individual components for proper functioning. Use appropriate testing tools such as multimeter to measure resistance, capacitance, and continuity. Test key components like voltage regulators, transformers, diodes, and capacitors. Replace any faulty components found during testing. Our next task is to repair and maintain the emergency light with the help of troubleshooting sequence block. Before starting any repair work, make sure you have the required tools. Ensure that the emergency light is disconnected from the power source to avoid any electrical shocks. If it has a battery, remove it as well. Check the emergency light for any visible physical damage, loose connections or burnt components. Look for broken wires, loose screws or any signs of overheating. Plug the emergency light into a power outlet and reconnect the battery. Verify if there is power reaching the light by checking if the indicator light turns on. If there is no power, check the power source itself, outlet or battery for any issues. Replace any faulty or burnt out bulbs with new ones. Make sure the bulbs are compatible with the emergency light. Examine the wiring for any loose or disconnected connections. Check if the wires are frayed or damaged. Check the circuit carefully before connecting the supply for any short circuit in the components or parts in the emergency light. Connect the main supply cable into ohm meter and check the resistance by switch on the circuit node to be connect with AC mains. Check for any open circuit visually or by ohm meter using testing for a short circuit. Analyze the status of the circuit by meters reading. If the emergency light is without short circuit fault, connect it to the supply mains and switch on. Check the symptoms of the unit and record the symptoms. If you find any issues, repair or replace the wiring is necessary. If the emergency light has a battery, use a multimeter to measure its voltage. Ensure the battery is fully charged and has a voltage within the specified range. If the battery is faulty or discharged, replace it with a new one. If the emergency light has a rechargeable battery, inspect the charging circuitry. Analyze the fault with the help of service flow sequence. Once you have repaired or replaced any faulty components, reassemble the emergency light. Connect it to the power source or insert the battery if applicable. Test the light to ensure it is working correctly. In this exercise, our third task is to test UPS and identify the faults and rectify. First of all, we have to read and interpret the nameplate details of the given UPS, type of UPS online or offline, model, power rating VA, change over time, battery rating, backup time. Switch on the UPS with UPS plugged in. Press and hold the on-off test silence button for more than 1 second until line normal LED green lights up, that is, UPS on and ready for use. If the green LED does not light up, the possible causes may be button not pressed or pressed too short, voltage of battery less than 10 volt, PCB failure, load may be less than 20 watt in battery mode. Identify the problem by self-testing UPS and rectify this fault by referring to the troubleshoot sequence block diagram. To switch off the UPS, press and hold the on-off test silence button for more than 3 seconds until the line normal or backup LED off. Check the condition of switch or backup LED, yellow LED, or press the switch for more than 3 seconds and rectify the problem if the UPS does not switch off. Press the on-off test silence switch more than 3 seconds to switch off the UPS and battery. Check the backup LED yellow. If the yellow LED backup lights off, the UPS and battery are in off position. If the back LED is not off, it indicates UPS is always in battery mode. The causes for this fault may be in the power cord, fuse, or abnormal voltage. The causes for this fault may be in the power cord, fuse, or abnormal voltage. Check the condition of the power cord, AC fuse, abnormal voltage, and PCB. Rectify the problem by referring to the troubleshooting sequence block diagram. Press the on-off test silence button less than 1 second when AC mains supply is available. Observe the operation of UPS. If the UPS operates on load in battery mode, then the battery LED lights up. It indicates UPS is on line operation. If the UPS does not operate on load on battery mode and immediately returns online operation and lights up the red LED, it indicates the backup time is too short, the battery is to be replaced or to be recharged. Recharge the battery immediately for at least 4 hours. Check and test UPS with recharged battery and rectify the fault by referring troubleshooting sequence block diagram. If the replace battery red LED is still on, replace the battery. Press the on-off test silence button for less than 1 second in backup mode. Observe the audible alarm, it should be silence. It does not function under low battery or overload conditions. Check the beeping alarm when pressing the silence button to stop the operation of UPS. If it is stopped in backup mode, it indicates UPS is in normal mode. But if the beep sound alarms continue, it indicates that UPS is overloaded. Press the button on or off during alarms to stop the beeping when the yellow LED backup lights up. Check for the maximum connected load to UPS and rectify this fault by disconnecting the excess until the beep alarm is not available. Task 4. Replacement of battery. Follow the instruction and procedure below for easy battery replacement. Unplug the unit from the AC power source and disconnect all connected equipment or load. Disconnect AC power cord from UPS unit. Turn the unit upside down and unscrew the 4 screws on top of the battery. Keep the screws in a safe place for reassembling. Turn the entire unit right side up by holding the top firmly. Lift top cover off and place to the side. The connection and electronics components will be exposed. Do not touch the inner components when changing the battery. Disconnect and remove the 2 leads, red and black, from the battery. You can remove the battery from the unit easily. Place the new battery in the same position or direction as the old one. Reconnect the leads, that is, red lead to positive position and black lead to negative position. Reconnect the equipment properly. Check the unit for its good condition and performance.
Recap. Let us just recap what you have learned so far. Analyze the defect of the voltage stabilizer. Repair and rectify the voltage stabilizer based on the defects. Identify the defects in emergency light. Rectify the defects by repairing the emergency light. Analyze the faults in the UPS. Rectify the faults by repairing the UPS. I hope you all understand how to test, analyze defects and repair voltage stabilizer, emergency light and UPS. Let us meet again in the next session. Thank you students and bye. Greetings students, in this session of the electrician trade you will be taught how to maintain, service and troubleshoot battery charger and inverter.
You'll be able to use it at the end of this exercise. Identify the defects in the inverter. Rectify the inverter by repairing. Troubleshoot and identify the defects in a battery charger. Repair and do the maintenance of battery and inverter. Let us take a look at the tools and instruments required for maintaining, servicing and troubleshooting battery charger and inverter. Tools or instruments. Trainees toolkit 1 set. Soldering iron 35 watt by 250 volt 1. Desoldering gun 65 watt by 250 volt 1. Star screwdriver set 1 set. Ammeter 0 to 10 ampere MC 1. Voltmeter 0 to 50 volt MC 1. Digital multimeter 31 by 2 digits 1. Equipments or machinery. Auto transformer 0 to 270 volt 5 ampere 1. Step down transformer 240 by 40 volt 300 volt 1. Charger transformer with center tapping 6 volt 0 6 volt 500 milliampere 1. Sealed maintenance free battery 6 volt by 120 ampere hour 1. Relays double pole 3. Materials or components. PCB 115 general purpose 2. Push button switches 2. Toggle switches 250 volt by 6 ampere 2. Diodes 1N4002 4. Diodes for bridge 1N112 4. Capacitors 250 microfarad by 12 volt 1. Resistors 10 ohm 1 watt 1. Pot 1.5 ohm by 10 watt 1. Low voltage lamp 6.3 volt 1. Fuse 250 milliampere 1. Neon lamp 1. Buzzer 250 volt 1. Soldering flux and 60 by 40 solder as required. Diode IN5402 3. LED red and green 1. Transistor 2N3055 1. Resistor 2.2 ohm 22 ohm 50 ohm 1 each 1K 1 watt 2. Electrolytic capacitors 1000 microfarad by 25 volt 10 microfarad 25 volt 2 numbers each 2.2 microfarad by 250 volt 1. Relay NC or NO 6 volt 1. Transformer 240 volt by 7.5 0 75 volt 2 ampere 1. Inverter transformer iron core laminated SWG 25 turns primary and 36 SWG 285 turns secondary 1. Fuse 2.5 ampere 0.5 ampere 1 each. SP switches toggle 6V 2. Let us take a look at the preparations for maintenance, servicing and troubleshooting of a battery charger and inverter. In this exercise, our first task is to service and troubleshoot of battery charger. Ensure your personal safety by wearing appropriate protective gear such as gloves, safety glasses and an anti-static wrist strap if necessary. Find a well-ventilated area with proper lighting for troubleshooting. Ensure you have a clear workspace and access to a power source for testing the charger. Keep a fire extinguisher nearby as a precaution. Make sure the charger is unplugged before starting any work. Familiarize yourself with the charger's user manual. It will provide specific instructions on operation, troubleshooting and safety precautions for that particular model. Gain a good understanding of how the charger works, including its components, voltage ratings and charging algorithms. This will help you troubleshoot any issues that may arise. Collect the necessary tools and equipment for servicing and troubleshooting. Examine the battery charger for any visible signs of damage or loose connections. Check the power cord, input and output terminals, control knobs and display for any issues. If you notice any physical damage, note down the repairing. Trace the battery charger circuit as shown. Check the circuit for an availability of charging volt at battery connecting terminals. If the voltage is not available, check the fuse provided in the fuse carrier. Test the voltage output at the bridge rectifier output with a multimeter. Check the conditions of bridge rectifier diodes. If found defective, replace them. If all the diodes are okay, check the AC input to the bridge network. Check the charging control circuit for normal working after the charging circuit is repaired. Check the auto cutoff of AC mains is off when the battery is fully charged. If auto cutoff is not working or functioning, check the diode connected to the potentiometer and voltage at relay terminals. And if the voltage is present at relay terminal, we can conclude that the auto cutoff is okay. Check the conditions of the battery Fully charged battery will show DC voltage is no load about 20% more than the rated voltage. Remember, do not allow the battery voltage no load drop below 70% of the rated voltage. If it is so, then reviving the battery is difficult. While charging the battery, you have to ensure that it is topped up with distilled water and caps are removed for easy gaseous out of the cells. Our next task is service and troubleshoot of inverter circuit. Understand all available information about the inverter circuit, such as its specifications, operating conditions. Understanding the design and functionality of the inverter will help you diagnose problems more efficiently. Before working on any electrical circuit, ensure your safety by following proper procedures. Make sure the power supply is disconnected and take necessary precautions to avoid electrical shocks. Use appropriate personal protective equipment (PPE) like gloves, safety glasses and insulated tools. Conduct a thorough visual inspection of the inverter circuit and its components. Look for any signs of physical damage, loose connections, burned or melted components or discoloration. Pay close attention to the capacitors, diodes, transistors and any other critical components. Trace the inverter circuit and locate the active components. Carry out short circuit and open circuit tests. Remove the battery. Connect to AC voltage and check the inverter output with the mains on. If there is no output, check the continuity of the inverter transformer's primary and secondary windings. If the transformer is OK, then check the transistor 2N3055 and the base supply. Check the fuse provided with NC of relay and check the conditions of relay contacts. Check the rectifier diodes and bleeder resistor connections. Check the mains transformer primary and secondary windings. Check the main fuse. Once the repair is completed, check the output voltage without battery connections. Connect the charged battery if output is available and operate it and ensure it's working.
Recap. Let us just recap what you have learned so far. Identify the defects in the inverter, rectify the inverter by repairing, troubleshoot, and identify the defects in the battery charger, repair and do the maintenance of battery and inverter. I hope you all understand how to maintain, service and troubleshoot the battery charger and inverter. Let us meet again in the next session. Thank you students and bye.
Greetings to all. In today's video, we are going to learn how to install an inverter with a battery and connect it to domestic wiring for operation. Objectives. At the end of this video, you will be able to: number 1. Select the proper rating of the inverter to install. Number 2. Select a suitable place for the inverter in the house. Number 3. Select the correct rating of the battery and the place to keep the inverter. Number 4. Install the inverter and make a connection to the load. Number 5. Test the inverter for its good performance on and off the supply mains. Let us collect the tools, materials and equipment required to do this practice. 1 trainee's toolkit, 1 portable electric drilling machine 6 mm, 1 star head screwdriver set of 6 mm, 1 roll jumper number 8, 1 combination plier 150 mm, 1 set double-ended spanner set 6 mm to 25 mm, 1 ball peen hammer 0.75 kg, 1 single phase energy meter 250 volts 10 amperes, 1 multi-pin socket 3x5 pin 250 volts 6 ampere, 1 800 volts ampere 250 volts inverter, 1 battery 12 volts 120 ampere hours, 1 2-pole MCB 10 amperes, 1.5 square millimeter PVC copper 1/18 wires as required, MCB single pole 6 amperes 2 number, auto wires stranded red and black each 1 number. How do I select the capacity of an inverter and battery? Let us assume we must design an inverter for the loads given below. From the tabulation, the total power that the inverter must supply the AC power is 740 watts. To calculate the inverter capacity in volts per ampere, we must consider the power factor. Substitute the values of watts and power factor as 740 and 0.8 respectively. Since for ohms the power factor of 0.8 is standard. So, the power required for the inverter in volts ampere for the given load is 925 volts ampere. Select the next range of 1000 volts ampere or kilovolts ampere. Let us discuss how to calculate the battery backup time. Let's assume you have an inverter battery with 120 ampere hour capacity, 12 volts of input voltage and 80% discharge efficiency. Substitute the value in the formulas. Backup time is equal to 120 into 12 into 0.8 by 740 is equal to 1.55 hours. Approximately 1 hour 30 minutes or 90 minutes. Procedure. Task 1. Select Install inverter with battery to connect in domestic wiring. Step 1. Select the suitable rating of the inverter considering the total connected in that house like fan, lamp, etc. The rating of the inverter should not exceed 60% capacity of the inverter key. For a 100 watts inverter, total load should not be more than 60 watts. Step 2. Select the right place to install the inverter where good ventilation is available. The place for installation for inverter should be nearer to the double pole switch and the energy meter position. Step 3. Select the correct place to install battery which is nearer to inverter and to the ventilation. Step 4. Install the inverter and battery close to each other. Do not provide the battery away from the inverter. It should be close to the inverter because it helps in reducing the current loss due to resistance of wire. Step 5. Make wiring connection to the inverter with 1.5 square millimeter wire. Step 6. Connect the 3-pin output socket from the mains supply. Step 7. Connect the positive terminal of the battery, that is, red wire, to the place provided for the positive terminal on the inverter. Step 8. Connect the negative terminal of the battery, that is, black wire, to the place provided for the negative terminal of the inverter. When connecting battery terminals to the inverter, use special auto wires. Do not use common 3x20 or 7x20 wires and ensure that the battery is fully charged. Step 9. Put grease or Vaseline on the battery terminals for reducing the terminal corrosion. Step 10. Complete the connection. Take the output from the inverter output socket and use it to power the load. To connect the inverter output to the load, use only 1x18 wire and do not use 3x20 or 7x20 wire. Step 11. Connect the on or off switch on the wall panel from the phase output pin of the inverter output socket. Step 12. Connect one common neutral line of both inverter output and mains AC supply. Step 13. Connect only one wire for the phase line from the inverter output socket to the switches. Step 14. Give connection to one bulb, one fan A and 2-pin socket only to the inverter output. Step 15. Connect the other devices in the room, that is, the tube light, fan B and 3-pin socket directly to the mains AC line. Low voltage load only to be connected on the 2-pin socket during the power off time. Heavy load should not be connected to this socket. such as heater, geyser, motors in HP, etc. Step 16. Check the operation of the inverter during power off and then power returns. If the main supply is on, the load connected to the inverter will get the main AC supply, and other devices which are directly connected on the mains AC supply will also work on the main supply. During power shutdown, the devices which are directly connected to the mains AC will stop functioning, and the devices connected to the inverter will keep on working on the inverter output. When the mains AC supply returns, the inverter will again connect the load to its output. In the video, we have discussed how to select the proper rating of the inverter to install, select the capacity of the inverter and battery, calculate the battery backup time, install the inverter with battery to connect to domestic wiring, and test the inverter for its good performance on and off the supply mains. I hope after watching this video, you can select, install, wire up and test the inverter with a battery for domestic wiring. Thank you and have a good day. Hi everyone. In today's video, we are going to discuss the thermal power plant and identify the functions of different layout elements. Objectives. At the end of this video, you will be able to number 1. Visit the thermal power plant and identify the various stages in the plant. Number 2. Interpret the function of each stage of the thermal power plant. Number 3. Prepare and draw the schematic diagram of the thermal power plant. Note: trainees may visit the nearest thermal power plant to visit the various stages of the power station and learn the functions of each stage from the plant engineer. Before entering the power station, the trainees should be aware of the safety rules and regulations prescribed for the plant areas, like wearing personal protective equipment, not touching any power lines, not touching rotating machines, etc. Let us discuss on thermal power plants. A thermal power plant in the world, thermal plants produce roughly 60% of the world's electricity. Coal, natural gas or oil-fired boilers are used to heat water and generate steam. The steam is then used to turn a turbine which is connected to a generator that produces electricity. It is necessary to cool the steam after it leaves the turbine, condense it back into water and then circulate it through the system. In India, the electricity generated by thermal power plants accounts for up to 71% of the total power generation. Now let's discuss each part of the thermal power plants. Step 1. Visit the stages of a thermal power plant. A. Coal and ash handling arrangement. Number 1. Tipplers in the coal handling factory unload the coal from the coal wagons. Number 2. Conveyor belts are used to move this coal upward to the coal storage bunkers. Conveyor belts are used to transfer the coal to the crushing house, where it is broken into small pieces and light dust is extracted. Number 3. Coal feeders then deliver the crushed coal to the bowl mill. Coal is processed into powder in a bowl mill. Coal particles fall on a circular metallic table inside the mill. A mixture of hot and cold air is then used to transport the crushed coal through coal pipes to the boiler. Ash handling arrangements. Ash handling systems are mechanical devices that correctly dispose of the ash. So after the coal has been burnt, the ash from the coal is collected and disposed of. Before disposing of it, it must be cooled down to a manageable temperature. It is then transferred to a disposal or storage area and used in various industries such as cement plants, construction and other similar places. The residual product, which may contain ashes or gases, will be collected by an electrostatic precipitator, that is ESP, and stored in the hoppers at the bottom of the ESP. B. Steam generating plant. A steam power plant consists of a boiler, steam turbine, and generator, and other auxiliaries. The boiler generates steam at high pressure and high temperature. The steam turbine converts the heat energy of steam into mechanical energy. The generator then converts the mechanical energy into electric power. C. Steam turbine. A steam turbine is a machine that extracts thermal energy from pressurized steam and uses it to do mechanical work on a rotating output shaft. The steam turbine is a machine that, categorized as a form of heat engine, can extract thermal energy from steam and convert it into rotatory motions. D. Alternator. The alternator used in thermal plants are termed as turbo alternators, as they are coupled to steam turbines. Turbo alternators have cylindrical rotors, hence a uniform air gap exists between rotor and the stator. Steam heat energy is converted into mechanical work by the turbine, and mechanical energy is converted to electrical energy by the alternator. Three-phase turbo alternators operating at a frequency of 50 Hz. E. Feed water supply. Feed water is water that has been purified or heated before being given to boilers to produce hot water and steam. Boiler feed water is the water that is given to the boiler and turned into steam. F. Cooling arrangement. Condenser and cooling towers make up the majority of the cooling system. In order to increase the power plant's overall efficiency, the condenser is utilized to condense the steam exhausted from the turbine. Step 2. Identify the following constituents of a steam generating plant and write down their functions in table. Constituents: A. Boiler. Type: ultra high pressure boiler, 13.7 megapascal, less than equal to pressure less than equal to 16.7 megapascal. Function: boiler is an enclosed pressure vessel in water, is converted into heat by gaining from the coal. Here, combustion takes place at 1300 to 1700 degrees Celsius. Superheater. Radiant type. Superheaters and reheaters are specially designed to increase the temperature of a saturated steam and to help control the steam outlet temperature. C. Economizer. Non-condensing type. An economizer is the device in which the waste heat of the flue gases is utilized from heating the feed water. D. Air preheater. Regenerative type. The main function of an air preheater is to extract excess heat from the flue gases in the boiler. E. Condenser. Surface condenser. A steam condenser is a closed vessel heat exchanger that is used to convert low pressure steam into water. It works to achieve two main objectives: to supply pure water to the hot well. Water from the hot well is again pumped into the boiler with the help of a boiler feed pump to maintain pressure below the atmospheric pressure at the outlet of the steam turbine so as to obtain the maximum possible energy. F. Cooling tower. Induced draft cooling tower. The purpose of a cooling tower is to reduce the hotness of water steam by expelling high temperatures from the water and then transmitting them to the air. Water treatment chamber. Reverse osmosis. Chamber filtration removes various particles from water. The feed is transferred from the feed tank into the chamber filtration unit where the water is filtered. Chamber filtration removes various particles from water. The feed is transferred from the feed tank into the chamber filtration unit where the water is filtered. Thermal power facilities use water treatment to avoid issues including carryover to turbine components as well as corrosion and scale formation or deposition in the boiler and turbine systems. Step 3. Trace the various parts of alternator and note down the nameplate details. Number 1. Number of phases 3. Number 2. Capacity 100 kilovolt ampere. Number 3. Speed 3000 revolutions per minute. Number 4. Output voltage 440 volt. Number 5. Current 250 amperes. Number 6. Frequency 50 Hz. Number 7. Excitation current 36 amperes. Number 8. Serial number Number 9. Year of manufacturing 1996. Number 10. Model number. Step 4. Draw the schematic diagram of thermal power station you visited. In this video, we have discussed the layout and different parts and equipments in a thermal power plant. I hope after watching this video, you can identify the parts in a thermal power plant. Thank you and have a wonderful day. Hello everyone, in today's video, we are going to discuss hydroelectric power plants. Objectives. At the end of this video, you will be able to number 1. Visit the various stages of a hydroelectric plant. Number 2. Interpret the functions of each hydroelectric plant. Number 3. Prepare and draw the schematic diagram of the hydroelectric plant. Let us discuss hydroelectric power plants. Hydroelectric power stations are generally located in hilly areas where dams can be conveniently built and large water reservoirs can be obtained. From the dam, water is led to a water turbine. The water turbine captures the energy in the falling water and changes the hydraulic energy, that is, the product of the head and flow of water, into mechanical energy at the turbine shaft. The turbine drives the alternator, which converts mechanical energy into electrical energy. Hydroelectric power stations are becoming very popular because the reserves of fuels, that is, coal and oil, are depleting day by day. The potential energy in the water held in the dam is transformed into kinetic energy of water in hydroelectric power plants. The turbine at the base of the dam is supplied with swiftly moving water from the dam. The turbine is propelled by the kinetic energy of the moving water. The generator is then propelled by a turbine to produce power. In terms of hydroelectric power capacity installed, India is 5th in the world. India had installed utility-scale hydroelectric capacity of 46,000 megawatts as the end of March 2020, or 12.3% of its total utility power production capacity. Step 1. Visit the stages of a hydroelectric power plant. That is, number 1. Hydraulic structures. Number 2. Water turbines. Number 3. Electrical equipments. Step 2. Identify the following stages of a hydroelectric plant and write down their functions. Hydraulic structures in a hydroelectric power station include dam, spillways, headworks, surge tank, penstock, and accessory works. Constituents: dam. Type: diversion dam. Function: a dam is a higher barrier which stores water and creates waterhead. Dams are built of concrete or stone masonry, earth, or rock fill. The type and arrangement depends upon the topography of the site. Constituents: spillways. Type: subsidiary spillways. Function: there are times when the river flow exceeds the storage capacity of the reservoir. Such a situation arises during heavy rainfall in the catchment area. In order to discharge the surplus water from the storage reservoir into the water on the downstream side of the dam, spillways are used. Constituents: headworks. Type: storage headworks. Function: the headworks consist of the diversion structures at the head of an intake. They generally include booms and racks for diverting floating debris, sluices for bypassing the debris and sediments, and valves for controlling the flow of water to the turbine. Constituents: surge tank. Type: restricted orifice surge tank. Function: a surge tank is located near the beginning of the conduit. When the turbine is running at a steady load, there are no surges in the flow of water through the conduit is just sufficient to meet the turbine requirements. However, when the load on the turbine decreases, the governor closes the gates of the turbine, reducing water supply to the turbine. The excess water at the lower end of the conduit rushes back to the surge tank and increases its water level. Thus, the conduit is prevented from bursting. Constituents: penstocks. Type: high density polythene. Function: penstocks are open or closed conduits which carry water to the turbines. They are generally made of reinforced concrete or steel. The thickness of the penstock increases with the head or working pressure. Various devices such as automatic butterfly valve, air valve, and surge tank are provided for the protection of penstock. Constituents: tail race. Type: mill race. Function: the tail race is the channel which carries water known as tailwater away from the powerhouse after it has passed through the turbine. It may be the natural stream channel or a specially excavated channel entering the natural stream at some point downstream from the powerhouse. Constituents: draft tube. Type: conical draft tube. Function: the draft tube converts the kinetic energy of the water into static pressure at the turbine's output. It is typically located near the exit or exhaust of the turbine. This keeps the water's kinetic energy from dissipating as it passes through the turbine's output. Constituents: turbine. Type: impulse turbine. Function: water turbines are used to convert the energy of falling water into mechanical energy. The principal types of water turbines are impulse turbines, reaction turbines. Number 1. Impulse turbine. Such turbines are used for high heads. In an impulse turbine, the entire pressure of water is converted into kinetic energy in a nozzle, and the velocity of the jet drives the wheel, that is, Pelton wheel. It consists of a wheel fitted with elliptical buckets along its periphery. Number 2. Reaction turbines. Reaction turbines are used for low and medium heads. In a reaction turbine, water enters the runner partly with pressure, partly with velocity head. The important types of reaction turbines are: number A. Francis turbines. B. Kaplan turbines. Step 3. Note down the speed of the water turbine and other details and enter it in the diary. Step 4. Trace the various parts of alternator and note down the nameplate details in table. Number of phase 3. Capacity 5 megawatts. Speed 1000 revolutions per minute. Output voltage 440 volts. Current 800 amperes. Frequency 50 Hz. Excitation current 100 amperes. Serial number: year of manufacturing 1986. Model number. Step 5. Draw the schematic arrangement of a hydroelectric power station. Step 6. Note down the mean step-up transformer specifications and the type of cooling arrangements. Step 7. Ensure that the cooling arrangement of a power transformer is cooling down or any other types. Step 8. Note the transmitting voltage range and the number of transmission lines. Step 9. Note down the total installed capacity of the power station and maximum number of turbines working together at peak load hours. So far, we have discussed the various stages of a hydroelectric plant and interpreted the functions of each hydroelectric plant. Thank you and have a good day. Hi everyone, in today's video, let us discuss identifying various equipments and their functions installed in a distribution system by visiting a nearby substation. Objectives. At the end of this video, you will be able to: number 1. Visit and trace the transmission and distribution lines of the substation. Number 2. Identify the equipment in the sequential stages of the distribution substation. Number 3. Prepare the layout and draw the single line diagram of the transmission and distribution substation. While visiting the substation, trainees should follow the safety rules and regulations as prescribed in the nameplates on equipment. Wear personal protective equipment and not touch any equipment without permission from the plant engineer. Step 1. Visit the transmission and distribution main substation. Step 2. Identify the sequential stages of transmission or distribution substations. Step 3. Trace and identify the various equipments like transformers, feeders, circuit breakers, isolator, CT and PT, etc. from the generator to the consumer points in sequence of transmission and distribution substation. Step 4. Note down the earthing system, the major substation provided with system earthing. Note the different values of earth resistance displayed in the earth pit. Note down which equipment or installation requires the least earth resistance value and irregular value. Identify the hollow conductors used for connection between feeders. Name of the equipment: transformers. Specification: 3-phase, 2 megavolts ampere, 11 kilovolts step down, 415 volt star-to-star connection. Function: a power transformer in substation is to change voltage levels between high transmission voltages and lower distribution voltages, or at the interconnection of two different transmission voltages. Substation transformers are constructed for indoor or outdoor mounting on a concrete pad, with high and low voltage cables entering operating compartments through enclosed sidewall mounted bushings, unit type transformers, or through cover or sidewall mounted bushings, open type transformers. Feeders: ring main type, 200 amperes, 11 kilovolt. A feeder transmits power from the generating station or substation to the distribution points. Since a feeder does not have immediate tapping, the current flow is usually the same for both the receiving and sending sections. A feeder is a conducting device used for transmission to the main load center. Primary power lines: 400 kilovolt. Primary lines connect plants to receiving stations and are usually made up of reinforced aluminium conductors. It receives the power from EHV lines at 400 kilovolt, 220 kilovolt and 132 kilovolt, and transforms the voltage to 66 kilovolt and 33 kilovolt to suit the local requirements in respect of both local and distance to ultimate consumers. Current transformer: 205 ampere. The lines in substations carry currents in order of thousands of amperes. The measuring instruments are designed for low values of currents. Current transformers are connected by lines to supply measuring instruments and protective relays. For example, if a 100/1 ampere CT is connected to a line carrying 100 ampere and then the secondary current of CT is 1 ampere. Circuit breakers: air blast circuit breaker, 132 kilovolt, 200 amperes. Circuit breakers are used for opening or closing a circuit under normal as well as abnormal conditions. There are different types of CBS which are generally used are oil circuit breaker, air blast circuit breaker, vacuum circuit breaker and SF6 circuit breaker. Bus bar: 66 kilovolt, 100 amperes. When the number of lines operating at the same voltage levels need to be connected electrically, bus bars are used. Bus bars are conductors made of copper or aluminium with very low impedance and high current carrying capacity. Lightning arresters: 11 kilovolts. Lightning arresters are protective devices used to protect equipment from lightning strokes. They are located at the start of the substation and are also provided near the transformer terminals. Ground wire: 8 SWG. Ground wires or earth wires are bare conductors supported at the top of transmission towers. Ground wires normally do not carry current, therefore, they are often made of steel. Disconnect switch: 200 amperes, 11 kilovolts. Disconnect switches are normally used to provide a point of visual isolation for the substation equipment during maintenance. Typically, a disconnect switch would be installed on each side of a piece of substation equipment to provide visible confirmation that the power conductors have been opened for personal safety. Overhead lines. 25 square millimeter aluminium conductor steel reinforced. An overhead line is the electrical cable and associated equipment that are used to transmit power between a generation plant and the transmission and distribution grid or to connect substations. Control building. A control house provides a weatherproof and, if required, environmentally controlled enclosure for supplement substation equipment. Additional space can be provided for workshops, equipment testing and repair, storage areas and lavatory facilities. Overcurrent relay and earth fault relay. 415 volt, 3-phase, 200 amperes. Overcurrent relays are electrical protection devices that are designed to open or trip a circuit when the current flowing through it exceeds a certain level, but on higher side. There are several different types of overcurrent relays, each of which is suited for a specific application. Step 5. Locate the places of equipments and draw the single line diagram of transmission and distribution substation which you have visited. Number 1. Incoming lines. 2. 110 kV. Number 2. Outgoing lines. A. 1. 110 kV. B. 4. 11 kV. Number 3. Transformers. A. 2 number of 100 megavolt ampere, 110 by 11 kilovolt, delta to star connection. 1 number of 2 megavolt ampere, 11 kilovolt by 415 volt, star to star connection. 110 kilovolts duplicate bus bar, 11 kilovolts single bus bar shows the positions of CTS, PTS, isolators, lightning and arresters, circuit breakers. Number 1. Incoming lines 11 kilovolts. Number 2. Circuit breaker, vacuum circuit breaker 11 kilovolts. Number 3. Transformer, step down transformer, delta, star 11 kilovolts, 400 volts. Number 4. Circuit breaker, air circuit breaker 400 volt. Number 1. Incoming line 11 kilovolt. Number 2. Lightning arrestor. Number 3. Transformer, step down 11 kilovolt, 415 volts, delta, star. Number 4. Circuit breaker, low tension circuit breaker. Number 5. Distribution box, distribution lines to consumers. So far, we have discussed, visit and trace the transmission and distribution lines of the substation, identify the equipment in the sequential stages of the distribution substation, and prepare the layout and draw the single line diagram of the transmission and distribution substation. I hope after watching this video, you can identify the equipment in the substation. Thank you for watching. Have a good day.
In this small video, I would like to discuss regarding the acceptance criteria of strength for concrete as specified in IS 456. One major aspect as far as strength is concerned, we should remember that the strength what is mentioned generally is a characteristic compressive strength.